Okay. Quick announcements. Homework is due tonight. As I said, if you can't get it done tonight, only drawback is you won't get your small bonus. It's not that big of a deal, but do try to get it in within the next week. If at all possible, we want to grade these and post solutions as fast as we can. And also the first discussion section is tonight at 3:30 in Curry. I think it's G502. I put it on Sakai. And like I said, totally optional, but if you want additional help with R, if you just have some homework questions, you're welcome to attend. So today we're discussing probability. I'm only devoting one lecture to this, and there's going to be some problems on the third homework, just because, a lot of what we do in statistics boils down to probability, so it's important to understand the basic concepts. But again, this isn't one of the really fundamental topics of the course that's going to be emphasized extensively. So if it's 10 billion formulas and your head's ready to explode, don't panic too much, but do try to at least understand the most important principles. As I said, like hopefully most of you have seen probability before and understand the basics. We'll come up with a rigorous definition and show how it can be calculated in a number of cases. The main emphasis here is the concepts rather than all the nitty-gritty of the formulas. So first of all, some terminology in terms of how to define probability. We define something called the sample space. That's the set of all possible outcomes, and then events are some subset of the sample space, which may be an excessively stuffy definition, but for precision, we need to go through this, but it's not something that I'm really going to expect you to know. But just some examples so you have the basic idea of how this works. One simple example would be gender. In this case, the sample space consists of two possible outcomes, male and female, and there's a number of different possible events for these two outcomes. One possible event is male or female, or you could also be either gender or neither gender. All of these are possible subsets of the sample space, and if we were randomly selecting a person from this class, we could talk about the probability of selecting someone male or someone female, or either or neither. Another example would be like letter grades in an undergraduate course. Your sample space would be A, B, C, D, and F, and you can talk about various events that would be subsets of that sample space. You can talk about the event where you earn an A, an event where you pass the class, that is, get any grade other than F, so the subset is A, B, C, D, or an event where you get at least a 2.0 GPA, which would be the subset containing A, B, and C. Hopefully straightforward enough. And probability, at least the simplest definition, is it's a numerical quantity that expresses the likelihood of an event. By convention, you can denote the probability of a given event by P of A. So the kind of canonical example of probability is you toss a fair coin. If you toss one coin, the sample space consists of two possible outcomes, namely heads and tails, and in this case the probability of heads would be equal to the probability of tails, which would be 1/2. You could make the event slightly more complicated and toss two coins. In that case, there's four possible outcomes. You can get heads, 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 tails, tails, heads, tails, tails. And again, you can define possible events and corresponding probabilities. That a probability of getting exactly two heads would be 1 out of 4 in this case. There's one outcome where you get two heads versus four possible outcomes, so you could talk about the probability of getting at least one head. If could be 3 out of 4 because 3 of the 4 outcomes you're getting at least one head. Or if, say, you're a Drosophila geneticist and 30% of your Drosophila are black because of a mutation, the other 70% are gray. In that case, your sample space consists of 2 possible outcomes, black and gray. The probability of black would be 0.3, the probability of gray would be 0.7. This just kind of illustrates that all events in your sample space don't have to have the same probability. And so what does this probability mean? Well, the simplest definition is that it's the long-term relative frequency of an event, that if the probability in an event is 0.2 and the event's repeated infinitely many times, then the event will occur, and the random occurrence is repeated infinitely many times, then the event A will occur 20% of the time over the long run. And I mean, some take issue with that definition, like if you say like the probability of rain tomorrow is 0.3, well obviously tomorrow is not going to repeat itself infinitely many times, and if it did, maybe it would be the same meteorological confluence, but yeah, that's way beyond what we need to care about here. At any rate, basic probability rules for calculating probabilities. 2 of the simplest ones, as I'm sure you're familiar with, is that probabilities are always between 0 and 1. The idea being an event with probability 1 is an event that always occurs, or an event with probability 0 is an event that never occurs, and hence that implies the probability of the entire sample space is 1. Because every event will always be a subset of the sample space. And in terms of terminology, you can talk about disjoint events are events that can't happen at the same time. That if you flip a coin, you can be heads or tails, but not both, or gender will be either male or female, but not both at the same time. They're disjoint. And non-disjoint events are events that can happen at the same time. If you're getting treatment for cancer, you could have surgery or you could have chemotherapy, but if you have one, that doesn't mean that you can't have the other. It's quite possible that you could have both. Likewise, if in a vaccine clinical trial, you could be vaccinated against the disease and you can be exposed against the disease, or both or neither sort of thing. And one of the simplest probability rules is that if A and B are disjoint events, then the probability of A or the probability of B is just the sum of the probabilities of the individual event. If you flip a coin and the probability of heads is 1/2, the probability of tails is 1/2, then the probability of heads or tails is 1 because it has to be either one or the other. Now, this only works if the 2 events are disjoint, which hopefully that's obvious, but this rule does get messed up all the time. I remember when I was younger watching the news one day and the meteorologist said in all seriousness, there's a 50% chance of rain tomorrow and there's a 50% chance of rain on Thursday, so there's a 100% chance of rain in the next 2 days. No, wrong. We'll discuss later on today how you calculate probabilities of A or B when they're not disjoint, but this rule only works if they're disjoint. So a simple example of this is letter grades once again. Since you can only get 1 grade in a class, then that implies that these events are disjoint. So we'll say the curve in the class such that 30% A's, 30% B's, 20% C's, and 10% D's and F's respectively. Then the probability of passing, which is equal to the probability of A or B or C or D, is just the sum of the probabilities of the individual events, or in other words, 0.9. Likewise, if you wanted to find the probability of getting a 2.0 or higher, which would be the probability of A or B or C, that sums up to 0.8. And another type of events that we can talk about are independent events, and two events are independent if knowing the probability of one event occurs doesn't change the probability that the other event occurs. Like if you toss a coin 2 times in a row, the fact that it was heads on the first toss tells you nothing about the probability of it being heads again on the second toss. Or in general, independence means the probability of the second event given the value of the first event is just the same as the probability of the second event when you know nothing about the first event. This is not the same thing as disjoint. In fact, if two events are disjoint, that implies that they're not independent, because if you toss a coin and event 1 is getting a heads, event 2 is getting a tails, then if event 1 occurs, then you know that event 2 cannot occur, which by definition means they're not independent if the probability of one event affects the probability of the second event. So, a couple examples of events that are not independent would be gender and prostate cancer. Kind of a silly example, but if gender equals female, then it's safe to say probability of prostate cancer equals 0. Likewise, smoking and lung cancer, the probability of getting lung cancer if you're a smoker is much greater than the probability of getting lung cancer if you're not a smoker.
So with the non-disjoint events, like you used the surgery chemo example, they wouldn't be independent, right? Because in that case, if you had surgery, maybe you wouldn't need chemo. Or am I like overthinking it?
The question was, do non-disjoint events, I guess what's the relationship between non-disjoint events and independence, and giving the example of surgery and chemotherapy, because if you have one, you're more likely to have the other. And the only thing I can say in general on that is sometimes they'll be independent and sometimes they won't. That, I mean, I'm trying, as you can tell, I haven't been sleeping enough. I can't think of an example off the top of my head. Say something like eye color and the type of shoes that you wear, just the first thing that's popping into my head, that if you wear a particular type of shoes, that most likely doesn't say anything about your eye color unless you're trying to match your shoes to your eyes, I don't know, but so in that case, they're non-disjoint, but they're still probably independent. The one thing that you can say is if they're disjoint, then they are definitively not independent, because if one event occurs, it implies the probability of the second event is 0. Yeah, and continuing on the example that I was giving here, that smoking and lung cancer, probability of lung cancer is greater if you're a smoker, hence smoking and lung cancer are not independent. And likewise, just lest we imply that dependence implies causation, that shoe size and test scores, to give one of my favorite examples, are not independent among children, that older children tend to have larger shoe sizes and higher test scores, so they're not independent, even though there's no causal relationship between the two. And two examples that are independent, like I said, heads on the first toss, heads on the second toss, they're unrelated to one another, or age and blood type, knowing that you're older most likely doesn't affect the probability that you have type O blood, because that would be another example of two non-disjoint events are the that are still independent, and or another example of an independent event that's something of a controversial one and contrary to popular belief. Say a basketball player hits 8 shots in a row, and the event is they hit their next shot. Well, I mean, anybody who watches basketball thinks in this case like, Jackson is on fire today, 8 shots in a row, better get him the ball. Well, they've actually done a statistical analysis of this and found that if you hit a bunch of shots in a row, the probability of making your next shot doesn't go up at all. That if anything, it goes down somewhat because the opposing team also believes in this hot hand theory, so the defense starts to collapse on him, so the probability the next shot goes down. And in other cases, it may be unclear whether or not events are independent, that one in the popular press that gets quite a bit of controversy, does watching violence on TV increase the probability of committing acts of violence in the future? Well, it depends on who you ask. Or another example is that patient has a disease that you're interested in, and when you do your genetic assay, that you get a missing value for a certain SNP. So in most cases, you hope that your assay, when it's missing, the missingness has nothing to do with the disease of interest. So any association test you do remains unbiased, but sometimes that's not the case. Maybe this SNP is really associated with the disease of interest, and maybe the call rate is higher for one version of the SNP than the other. In that case, the missingness and having the disease wouldn't be independent. Or the example I gave earlier in class, that say if you didn't do all your genotyping in the same place and you genotyped more of your cases at one location than the other, and there was mechanical variation in your assay such that one study site where you did the assays was more likely to have missing values. In that case, they would not be independent. So that's just an example of a case that may be somewhat more ambiguous. And probability rules for independent events, it's that if you know that events A and B are independent, then the probability that both A and B happens is just the probability of the first event times the probability of the second event. So if the probability of heads on the first toss is 1/2, the probability of heads on the second toss is 1/2, the probability of getting 2 heads in a row is 1/4. Well, I just gave my example without remembering the examples on the next slide. Okay, well, no need to say that again. Or another example of independent events is blood types that, say, for example, in the United States, this is pretty close to the actual distribution of blood types. That, as I'm sure you all know, there's 4 possible blood types, O, A, B, and AB, and you can also have Rh positive blood and Rh negative blood, and the blood type and the Rh factor are independent of one another. So I'll give a few examples of ways that you can calculate probabilities using that information. That, well, I guess not just independence, but also disjoint events. So say we wanted to figure out the probability of having type O blood. Well, since being Rh positive and being Rh negative are disjoint events to find the probability of having type O blood. That's going to be equal to the probability of being O positive plus the probability of being O negative. Because maybe I should have written this out a little further. Basically, the probability of type O blood is equal to the probability of O positive or O negative. And since those are disjoint events, that's equal to the probability of O positive plus the probability of O negative. So 0.384 plus 0.077 equals 0.461, consistent with what we see in the table. Or another possible example, say you wanted to know the probability of being Rh positive or Rh negative. Well, in that case, the probability of being Rh positive is 0.833, probability of being Rh negative is 0.167, which adds up to 1, which of course makes sense because you have to be either one or the other, so the probability that you're either one or the other is of course equal to 1. Oh, now a complement rule, which I guess I never spelled out explicitly, but the complement rule just says that given an event A, the probability of not A, i.e. the probability that A does not happen, is just equal to 1 minus the probability that A does happen. I guess that follows from the rule on disjoint events, but anyway, to illustrate that, if we wanted to calculate the probability of not having type O blood, that's obviously equal to the sum of the probabilities of having any blood type other than O, so the probability of A or B or AB. Once again, those three events are disjoint, so find the probability A or B or AB. You can just sum the individual probabilities. Sums to 0.539. But you could also get that using the complement rule. The probability of not O is equal to 1 minus the probability of O blood, which turns out to be 0.539. Same answer regardless of how you do it. And another example of disjoint events, if you wanted to find the probability of having B blood or O blood, you can just take the probability of B plus the probability of O. Turns out to be 0.572. So, now to illustrate how you can use the rule for independence, let's say that we want to find the probability of having O positive blood. Well, since Rh factor and blood type are independent, that's just equal to the probability of having type O blood, i.e. 0.461, times the probability of being Rh positive, which is 0.833. Multiply them, and after rounding, you get 0.384, consistent with what we see in the table. Oh, another way that you could use the independence rule is say that you have a married couple and you want to find the probability that the husband has type A blood and the wife has type B blood. You can say probability, that's just equal to the probability that the husband's type A times the probability of the wife's type B. In other words, 0.388 times 0.111, which is equal to 0.043. Or slightly more complicated examples, let's say we want to find the probability that one spouse is type A and the other spouse is type B. Well, there's two possible ways we could get that, and these two ways are both disjoint. You could have the husband type A and the wife type B, or the wife type A and the husband type B. And using, since those two events are disjoint, you can just say that's equal to the probability the husband's type A and the wife's type B plus the probability the husband's type B and the wife's type A. Using the same logic as we used on the previous slide, both of those probabilities is 0.043. So the probability of either outcome is 0.043 plus 0.043, which sums up to be 0.086. And just to illustrate the fact that the addition rule doesn't work if two events are not disjoint, if you wanted to find the probability that a person has type O blood or they are Rh positive, if we were to just mindly sum them together, we get 1.294, which is obviously wrong because we can't have probabilities greater than 1. So in this case, since the two events are not disjoint, you can't just sum the probabilities. So I'll show you how you compute the probability in this case here in a minute or two. In fact, I will do it on the very next slide. That in general, if you want to find the probability of A or B and they're not disjoint, then that's going to be equal to the probability of A plus the probability of B minus the probability of both A and B. The intuition here, if you draw the picture, that you want to find the probability of A or B, which represents the area inside of A or the area inside of B. So you take the area of A plus the area of B, but then you've counted this area in the middle, the overlap between the two groups, twice, so you have to subtract that off. Hence, the formula is probability of A plus the probability of B minus the probability of A and B. So, if the events are independent, then this becomes easy. The probability of A and B is just probability of A times the probability of B. If they're not, then things get a little bit more interesting. So, in the blood type example, if we wanted to find the probability of type O blood or Rh positive blood, that would be the probability of type O blood plus the probability of Rh positive blood minus the probability of type O blood and Rh positive blood, i.e. the probability of having O positive blood. So you go 0.461 plus 0.833 minus the probability of both, i.e. 0.384. That gives us 0.91, which is a more reasonable answer. And the next idea that we'll talk about is conditional probability, which it's denoted by this little probability B line A. You usually say that is the probability of B given A. Like the probability of heads on your second toss given heads on your first toss, or the probability of lung cancer given that you're a smoker, something like that. And as it turns out, the probability of B given A is equal to the probability of A and B over the probability of A. I could explain the whole intuition behind that, but it's probably more complicated than we need for the sake of this course. For the purpose of this class, if you just remember the formula, you're fine. So, simple example of these new rules is the canonical coin tossing example again. Say we have flipped the coin 2 times and define the events that A is the first toss is ahead, B is the second toss is ahead, and C is that at least 1 is ahead. Then, obviously, the probability of A is equal to the probability of B, which is 1/2. If we wanted to find the probability of C, which is the probability that at least one flip is ahead, Well, we can use the general addition rule. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which is equal to 0.5 plus 0.5 minus 0.5 times 0.5 since they're independent, so that's equal to 0.75. So my meteorologist that I saw on TV, the probability of rain either tomorrow or Thursday should have been 0.75 if you're willing to assume that the probability of rain on one day is independent of the probability of rain on the second day, which admittedly is a big assumption, but however you slice it, it's not one. So if you wanted to say, suppose in an illustration of conditional events, say that we're given that at least one of the coin tosses was ahead. We want to know what's the probability that the first toss was ahead. Well, in this case, we want a conditional probability that the first toss was ahead, given event C that at least one of them was ahead. So by the conditional probability rule, that's equal to the probability that the first toss is ahead and at least one toss is ahead, divided by the probability that at least one toss is ahead. Well, obviously, if the first toss is ahead, that implies that at least one is ahead. So probability of A and C is just equal to the probability of A. So the probability of A given C turns out to be the probability of A divided by the probability of C, which works out to be 2 out of 3. Oh, if we want to do the blood type example again, say we wanted to find the probability of type A blood given that a person is Rh positive, well, we can use the same formula. The probability of type A blood given Rh positive is equal to the probability of A positive blood divided by the probability of positive blood generally. So that's 0.323 divided by 0.833, which is approximately equal to 0.388. And note that 0.388 is just the probability of having type A blood generally. So probability of type A blood given Rh positive blood is just the probability of type A blood, since blood type and Rh factor are independent. In general, if A and B are independent, then the probability of A given B is just equal to the probability of A. In fact, that's the very definition of independent events. Yeah, basically just said this, that two events are independent if they both have positive probability, and the probability of B given A is equal to the probability of B. And the general multiplication rule, say you want to find the probability of A and B, we know that that's just equal to the probability of B times the probability of A if they're independent. If they're not independent, then the probability of A and B is equal to the probability of B given A times the probability of A. If you think about it, that makes intuitive sense that if you need both A and B to happen, then that's the probability, first of all, that A happens, then the probability that B happens given that A already happened. Obviously, this can go in the other direction as well. You could also say it's the probability that B happens times the probability of A happens given that B happens, sort of thing. And you'll notice that this is just the same. If you divide both sides of this equation by the probability of A, then you just get the conditional probability rule. The probability of B given A equals probability of A and B divided by probability of A. And this general multiplication rule works even if A and B are not independent. So, one final example illustrating how these probability rules work, that this is just kind of a fun example as much as anything. It's a really good way to mess with people at parties, and I've known really smart people get really upset at me and said that this had to be wrong, but I'll hopefully explain it. If you're not familiar with the Monty Hall problem, Monty Hall was the name of a game show host way back like the 50s or 60s or something, and the name of the game show I believe was Let's Make a Deal. I forget what it was exactly, but the basic gist of the game is that there's three doors, and behind one of the three doors there's a car, and behind the other two doors there's goats. And obviously you're hoping to get the door that has the car behind it. So at the beginning of the game, you have to just guess one of the three doors. And then once you pick a door, the Monty Hall would open one of the other doors to reveal that there is a goat behind one of the other doors that you didn't open. And then you were either given the option of keeping your original guess or switching to the other door that Monty Hall didn't open. So the question is, if you're on this game show, you choose door 2, Monty Hall opens door 1, says there's a goat behind it. Do you want to keep door 2 or do you want to open door 3? And I mean, most people's intuition is, well, I mean, it's a 50-50 chance either way. It doesn't matter whether you switch or not. Well, is that really the case? Let's write out the probabilities here and see if we can figure this out. So, the probability, if you don't switch, then the probability of getting a car is 1 out of 3. That's hopefully reasonably intuitive. So let's figure out the probability that you get a car if you do switch. Just for the sake of simplicity, let's say that you pick door 1 for your initial guess. So let's define some notation. Let's D3 denote the event that the host opens door 3, and let's let C2 denote the event that the car is behind door 2. So then the probability that the car, or the probability that the host opens door 3 is equal to the probability the host opens door 3 given that the car is behind door 2 times the probability the car is behind door 2 plus the probability that the host opens the third door given that the car is not behind the second door times the probability the car is not behind the second door. So probability that the host opens the third door given that the car is behind the second door is 1, because the host won't open the door that you chose, i.e. door 1. He also won't open the door that the car is behind. In that case, he has to open door 3, times the probability that the car is behind door 2 in the first place, which is 1 out of 3. Likewise, if the car is not behind door 2, then he's equally likely to open either door 2 or door 3, and the probability the car is not behind door 2 is once again 1 out of 3. So I guess that should actually be 2 out of 3. One way or another, it sums to 1/2. So the probability that the car is behind is behind door 2, given the host opens door 3, is equal to the probability that the car is behind door 2 and the host opens door 3 divided by the probability the host opens door 3, which then we can rewrite the top as the probability that the car is behind door 3, the host opens door 3, given the car is behind door 2, times the probability the car is behind door 2, divided by the probability the host opens door 3 generally. If I haven't totally confused you, the dust clears, you end up with 2/3. So in other words, if you switch doors, you double your chances of winning. And if your head exploded with all that conditional probability, a simpler way to look at it is if you just go back to the earlier premise here, that the probability of, on your first guess, the probability that you're right is 1 out of 3. Now, if you're right the first time, then the host will randomly pick one of the other doors. It doesn't matter. And if you switch, you lose. On the other hand, if you're wrong the first time, that implies that there's 2 doors remaining. The host will always pick the one that has the goat behind it rather than the car. So if you switch, you win. So the only way that you lose when you switch is if you were right the first time. So the probability of being right the first time is 1 out of 3. The probability of winning if you switch would be 2 out of 3. Here's an illustration of all these different scenarios that the car location is door 1, door 2, door 3. You write out all the probabilities. If you pick door 1 and the car is actually behind door 1, you lose if you switch. Otherwise, you win if you switch, so you end up with a probability of 2 out of 3. And yeah, I'm probably never going to ask you to do anything this convoluted in this class. There's a couple on the homework assignment that are a bit tricky, but nothing this nasty. This is just kind of a fun example that you can use if you want to mess with people at parties or whatever. Oh, things to remember for today's lecture: that the probability of an event is the frequency the event will occur if it's repeated infinitely many times. You can compute more complicated probability using these rules, and when you use these rules, make sure you keep the various independence assumptions in mind. Any questions about anything today? Okay. Like I said, try to get the homework done as quickly as possible. If you have any questions, feel free to email Erica or I, or set up a time to meet or whatever.